Today in the Physics Funhouse, we are investigating the brightness of light bulbs. Light bulbs, of course, are resistors, and the power dissipated in a resistor, that is, the electrical energy that is converted to thermal energy, is given by P equals I times V. The power is equal to current times voltage. And when we combine that with Ohm's law, we can express that in two different ways in terms of the resistance. One is P equals I squared times R. The other is P equals V squared divided by R. And so what I want you to notice is that these two light bulbs, they're connected to the same battery. Right now the battery is at 2.2 volts. And they're connected in parallel, so they should have the same potential. They should have the same voltage across them. And the bottom one, which is kind of a globe-shaped light bulb, is significantly brighter than the pointy one above it. If I drop the voltage down a little bit, maybe I'll be a little bit more evident. Let's turn it up a little bit. And so no matter what I click the battery on, you can tell, hopefully, that the globe light bulb is brighter than the pointy light bulb. And so the question we want to investigate today is that always going to be true? Will this light bulb always be brighter than this light bulb? So first, let's kind of do just one kind of light bulb at a time, and then we're going to come back and investigate both of these light bulbs together. So I'm going to turn this back down to 2.2. Get rid of this guy for just a second. And I'm going to replace it with this one. So this one is identical to this one. So these light bulbs should be exactly the same brightness right now. So right now they're connected in parallel. So they got the same voltage. Keep in mind how bright those guys are. And I'm going to reconfigure them to a series configuration. And so I'm going to move this wire over here. Set that right there, and then reconnect them. So now that they are in series, notice that they have the same brightness still, but that brightness is much less than it was before. And so the reason for that, you can think about it in two different ways. One, we can think about it that we reduce the current through each light bulb, and so less current times the same resistance, approximately, would give you a less bright light bulb. Or you could think about it in terms of potential. The potential across each light bulb would be less than it was before, because now instead of having the same potential that's equal to the battery, basically the sum of these two potentials has to equal the battery. And so by making V smaller, we also make P smaller. And so if we kind of look at the top expression of this, we're reducing both of these quantities actually. We're reducing the current because we made the resistance for the whole circuit larger by adding them in series, and we're reducing the potential because now the sum of the two potentials has to add up to the potential of the battery. So really there's two factors that are both reducing the power in the same manner. So both the current and the voltage are reduced. And so when I go from a series configuration to a parallel configuration, we can make the claim that basically the light bulbs got 4 times brighter because we both doubled the current and we doubled the voltage. And so that's the first thing we need to be able to do is go, well, what happens to these light bulbs if they're in series versus parallel with each other? Let's do this now. Let's add a third light bulb. So like, there's a third identical bulb. Let's see what happens if we put this bulb right here. So that current has to go through this bulb and then is split between these two bulbs. So notice that when I did that this bulb is medium bright, and these two bulbs are not very bright at all. In fact, they're so dull, dim, whatever you want to say, that you can't even see that they're on. They are on, and in fact, if I unscrew this one, well, you'll notice that this one got brighter. So by removing this one from the circuit, now I'm just back to that simple series circuit I was a few seconds ago. When I screw it back in, that light bulb got brighter, and this one got dimmer. And so the circuit that we're looking at here, we kind of draw it real quick. So the circuit that we're looking at is right here, where this bright one, labeled out with a B, is right there. And so the current that goes through the first bulb here has to then be split between these two here. And so if 1 amp of current went through that bulb, these guys right here would be splitting that 1 amp between them. So 0.5 and 0.5. When we when we take this one out of the circuit, now all the current that goes through this one has to go through this one and vice versa. So if I were to screw that one back in and then remove this one, I can up with that same series circuit. However, notice that this one gets dimmer because by removing a resistor in parallel, I am decreasing the equivalent resistance of the circuit. And so this light bulb is bright when both of them are connected, because there's two paths for charges to go through right there. But by removing one of them, I make the other one in that parallel configuration brighter. And so that's a very typical circuit for us to be able to be asked to analyze in AP Physics 1. So let's get rid of this guy. So next we're going to bring back our pointy light bulb. And again, when we just connect these two together to the same potential, the pointy one is not as bright. And so I can kind of compare those two a little bit using my equations. They have the same potential, so I can use this equation right here to kind of compare them. I notice that this one is brighter, and so a brighter light bulb with the same voltage as a less bright light bulb, I can make the claim that the brighter light bulb has a smaller resistance. And so if V squared over R gives me the power, then if I take the same V divided by a small r, I get more power, more P, which shows up as a brighter light bulb. And so here's the rub. This one is not always going to be brighter. I can say that this one has a lower resistance, but it's not always going to be a brighter light bulb. So what happens if I take these and put them in a series with each other? I'm just going to relocate this one here. When I connect them, you'll notice that this one is not very bright. It got dimmer. This one got way dimmer. And it may even look like it's not glowing at all, but it is glowing. If I unscrew it, I break the circuit and this one goes out. Screw it back in, that one comes back on. So this one is just not glowing very, very bright at all right now. I can try to increase the voltage to see if I can make it brighter. So now I can see it. I don't know if you can see it. Just barely glowing right there. So in comparing this circuit, I can't claim that they have the same voltage anymore. They still have to obey the loop rule. So the voltage across the pointy one plus the voltage across the round one equals the voltage across the battery. But I can claim that they have the same current now because they are in a series with each other. And so looking at the power equation this way, if I know they have the same current, then the bulb with the largest resistance has to be the brightest. So if I multiply the same current by a big R, I get a bigger P, which gives me a brighter light bulb. And so by connecting these in series with each other, like that, I make this one be the brighter of the two. When they were in parallel and they had the same voltage, the lower resistance bulb was brighter. In series, the higher resistance bulb was brighter. And so kind of thinking back in terms of Ohm's law, when I connect them in series with each other, they have the same current but not the same voltage. So if we connect them like this again, so I know the current going through this bulb and this bulb have to be the same, but they don't have to have the same voltage. And so by virtue of this one having a higher resistance, this voltage right here across the pointy one must be larger than the voltage across this one. And so just because a light bulb is brighter in one circumstance doesn't mean that it's brighter in the other. And as we change the elements of a circuit, we have to figure out what's changing about each of those individual resistors. And so that's kind of the gist of the lab that we're doing today. Under what conditions will this bulb be brighter? And under what conditions will this bulb be brighter? So when you go to the hardware store to buy new light bulbs for your house, and you look for, say, a 60 watt bulb, well, 60 watts doesn't really mean anything in a general context. In a specific context, that means that your light bulbs will draw 60 watts when connected to a voltage source of 120 volts. That's the voltage of the electrical outlets in your house. And so that 60 watts is not necessarily always going to glow the same brightness as 60 watts. It's going to be variable if you connect it to different sources. And so when you connect a light bulb to a 120 volt source, then you'll get the power output that's indicated on the light bulb. And so that's just kind of something to realize, is that 60 watts is very specific for the light bulb when you buy your light bulbs. I don't know how often you guys shop for light bulbs. Next time you're at the hardware store or the Walmart there, check them out and, you know, kind of see if you notice any difference. Okay, so our lab today is basically going to be to see if we can predict what's going to happen to the light bulbs in a bunch of different situations. Let's get started on that.